Okay, so today we're going to start talking about sequences and, well, probably not today, but series of functions as well. And I have this like tricky thing that I need to contemplate, and I think I'm going to make it a game time decision as to whether or not we talk about sort of Cauchy things. Because I didn't really talk about them that much when we did sequences. But whatever, we'll figure it out. Okay, so sequences and series of functions. Now, this is a pretty fun topic, but on the other hand, it's also a little bit more complicated because, as you can imagine, we're not just talking about sequences of real numbers anymore. When we start talking about sequences of functions, things become a little bit more complicated. And in part, the reason why it's going to become more complicated is because we're going to have multiple different notions of convergence. And of course, this gets worse. So the more analysis you do, the even more exotic different kinds of types of convergence you have. Weak convergence, weak star convergence, strong convergence, et cetera, et cetera, et cetera. The weak operator topology convergence. So we're not going to worry about most of that. Okay, but instead what we're going to do is let's sort of get the basics underneath us. So what I'm going to say is, let's just set up a bit of notation. So let's say notationally, that's not notationally, let, so r to the power of s, right? I think maybe we talked about this at the beginning of the year. Somebody remind me if we did though. This is just the set of all functions from s to r, right? This is all functions from s to r. And then we have, did we define that? I don't remember if we did. Somebody tell me if we did. So these are the functions f in r to the s, such that f is continuous. So it's the continuous functions on s, right? And then we might do like ck s. So that's the functions r in r to the power of s, such that f is ck, right? K times continuously differentiable. Just to make our lives a little bit easier, S could be like basically any subset in the real numbers. Here, let me maybe put this up here. So notationally, let S be just a subset of R. For our purposes, it's almost always going to be an interval, right? But in theory, you could do some things that aren't intervals. That would be okay. Okay, so where's my notebook? I guess we're going to start off with just the definition. So definition, let's say, given a fixed S, a fixed subset of R, a sequence of functions and maybe let's put in brackets here with domain S. So they should all have the same domain is basically what I'm kind of telling you here, right? Okay, when we talk about sequences of functions, implicitly everything's going to have the same domain. With domain S is any map, let's maybe call it F, from the naturals into R to the power of S. Okay, so let's take maybe just like a really quick detour there and say like, oh, what we mean by that. So example, right? You could have something like Fn being the map, I don't know, 0, 1. Oh yeah, we talked about this a little bit on Thursday. Right, so you can have something like that. So F1 is just the line x, F2 is x squared, F3 is x cubed, and so on and so forth, right? So you've got this index on your function. In some sense, like there's two variables going on here, right? There's your index, which is keeping track of where you are in the sequence, but then there's also your input variable x, which tells you, what number you're going to put in. So definitely kind of get used to seeing things like Fn of x like that. Okay, that's going to come up. And this is totally fine. You could do something like this. This isn't surprising. Okay, now, depending on your opinion, this is either we get, okay, let's say this. There's no such thing as an increasing sequence anymore, right? That doesn't make sense because we don't have a notion of an order on our set of functions, right? What does it mean for one function to be bigger than another function? We don't really have that. Same sort of thing, the notion of boundedness becomes a little bit tricky. There is kind of a thing that you can do there, but right now, maybe think about that on your own, see if you wanted to extend the notion of boundedness, what would that look like? So we don't have any of those things, which is nice. We can kind of throw those away. On the other hand, it comes at a price, right? The reason why we don't have to worry about those things is because stuff's more complicated. So we don't have to define any of that. One thing, though, that we should talk about is subsequences, but the definition of subsequence is the exact same. You take a strictly increasing function from the naturals to the naturals and look at f composed with that, right? So a subsequence is a choice of strictly increasing map from the naturals to the naturals. Let's call that little n. And the sequence f compose n. Right, so same sort of story. And again, don't get mired down in this idea of strictly increasing map. What you're saying is you're just selectively choosing some elements of your original sequence, but you have to preserve their order, right? That's what this map little n here is doing. It's saying we're going to pick out some of the elements of your original sequence. We have to maintain the same order of them, though. Okay, so that's all that's going on. So yeah, we could choose, maybe let's do a quick little example here. So from our previous example, so if Fn is as above, right, maybe we define something like F n k of x to be maybe like the, I don't know, let's take like the powers of 2 or something, right? X to the 2 to the k, something like that. Right? Do I want to write that? Yeah, maybe even just let me write it like that there as well. So each of these things certainly is one of the things above, right? It's x to the power of some natural number. But and they're still in the same order, right? X to the 4 comes before x to the 8, comes before x to the 16. But we don't include all of them, right? X cubed doesn't show up here because it's not a power of 2, or its exponent isn't a power of 2. So there would be a subsequence that we could take there. Now, from a notational viewpoint, we're going to indicate sequences of functions pretty much the same way that we do sequences of real numbers, right? So notationally, we write Fn, n equals 1 to infinity, to denote the sequence. And again, when the indices either aren't important or are implicit, then we just drop them, right? Or Fn when we're feeling lazy. And again, sort of implicit in all of this conversation is the fact that the domains here are all the same. And again, they're sort of understood, right? Like we've hidden it, but of course we know that part of the data when you specify a function is its domain, right? So the domain is there, it's understood, it's sort of obfuscated, but it's there all the same. All right. So here, let's do something. I had a picture here, or I guess actually first what we should do is let's define a notion of convergence. So when we first talked about sequences, we did a bunch of stuff where we talked about properties. Though, the interesting thing here is going to be convergence, right? That's the thing that we're worried about. So let's go straight to it. So definition. So a sequence of functions Fn, and again, I'm just going to kind of write it like this so that we, when it's not implicit what the domain is, we're going to have it. So a sequence of functions Fn mapping S to R is said to converge pointwise. And you'll notice here we've had to add on this extra sort of adjective, right? We're saying subsequences have to be increasing. Yes. So the increasingness of the subsequences guarantees that things occur in the same order, right, as the original sequence. Because otherwise, let's say here n of 1 was 7, but n of 2 was equal to 3, then you would have f of n1 is f7, but f of n2, the next element in the sequence, would be f3. And you're not allowed to go back in the sequence like that, right? You have to maintain the order. So the strict increasingness of the subsequence just guarantees that the elements actually do sort of successively follow one another, right? Like in some sense, most efficient strictly increasing map from the naturals to the naturals is just the identity map, right? It takes 1 to 1, 2 to 2, 3 to 3. Any other strictly increasing thing is going to have to map nk to something strictly bigger than k, right? And yeah, that strict increasingness just guarantees that we preserve that order. But again, like notice, we're not talking about the sequence it defines itself. We're talking about the indices, right? So in that case, we're talking about this function little n is keeping track of the indices of the subsequence. That map needs to be strictly increasing. It doesn't even make sense, though, to ask if a sequence of functions is an increasing sequence, because again, what does it mean for one function to be bigger than another? We can compare two functions at a single point, but right now we don't have a meaningful notion of saying like, oh, the function x squared is bigger than sine x. Like, what does that mean, right? We don't really know what that means. So if we've got a sequence of functions, we're going to say that not just that they converge, but they converge pointwise. If basically at every single point in S, I guess we should say converges pointwise to F. Oops, this is the wrong color. And F, of course, has to map the same domain as well. They converge pointwise to this function F if it's done, if like the Fn's converge to F at every point in S, right? If, oops, for every x in S, we get that the limit as n goes to infinity of the Fn's is equal to f of x, right? And that's true for every single one of these x's. Now, strictly speaking, we don't need to, for a fixed x, this is just a sequence of real numbers. The notion of convergence is our usual notion of convergence. So really, I shouldn't have to write down any epsilon, n definitions or anything like that. But it is worth writing down here because we're going to define another notion of convergence later. And really being able to see the difference between them is going to show up when we look at their formal definitions. So, the formal definition, right? Like this definition above is fine. It is a formal definition, but let's unravel what that limit means. So the formal definition is that Fn converges to F. And again, we're going to use this notation, right? Just like we did for sequences, is that Fn converges to F pointwise if, and now let me write this in mathy notation, for every x in S and for every epsilon greater than 0, there exists a natural number n such that for all n greater than or equal to n, f n x minus f x is less than epsilon. Okay, and whoa, just quantifier hell here. But the important thing that we're going to need to pay attention to, remember when we were talking about continuity and uniform continuity, right? The difference between those things was the dependency of the delta on what point we were working with. And we're going to have something similar here where right now, right, by the location of the x for every x and s there exists in n, means that n right now is allowed to depend on x. So note, therefore, that n here is allowed and generally will depend on x. Right? So if you choose a different x in your domain, that means that correspondingly, you're going to have to go a different, distance into your sequence in order to guarantee that you get within epsilon, right? So that's something that we're going to have to worry about. And what you can imagine is if you're sort of thinking, especially in our notion of uniform continuity, like what changed is that we're probably going to move that for all x in front of the n, right? So that the same n has to work for all x's. And that is going to be what, a different notion of convergence that we talk about later. But yeah, hopefully that makes sense. Let's do an example of convergence here, though, and maybe you can get a feeling for it. So let's do, again, sort of my classic example. And I actually did, I think I plotted this last time, but maybe let me just plot it again here. And I actually saved these. So just give me a second here. Where did I put it? Is this the one I want? No, I want this one. Okay, so let's say Fn map the unit interval 0, 1 to R be given by x maps x to the n. Right, so these are these examples that we had just introduced above. Let's show that this sequence converges. That's not sequence. Sequence converges to, and I suggested this sort of last time. So it's going to be 0 if x is not 1, and then 1 if x equals 1. Okay, so that looks like a sort of weird function. And I'm going to show you, again, I've sort of like put this into Desmos so we can see what this looks like. Yes. This is what I want, right? No, that's not what I want. There we go, Desmos. Right, okay. So here, we have to kind of filter through the Desmosian thing, but we've got our functions, right? Here, let me go back and set this to 1. So we've got our functions here. I've plotted this in whatever the heck this color is. And then I've got my other function, the thing that I'm claiming to limit to, I've sort of like drawn these in these blue dots, right? So it's the function which is 0 everywhere along the x-axis. But when we hit 1, we just sort of pop up to 1 here, right? And this is the great thing about technology, right? Back in the day, you imagine people just had to figure this stuff out. Is we just have to slide this thing here, and we see that what these functions are doing. And I mean, again, we kind of have an intuition for this. If you start with a number between 0 and 1 and you raise it to like the 40th power, right? We know that when you take numbers between 0 and 1, raise them to big numbers, they get really, really small. So the curve begins to like hug the x-axis, right? So it begins to hug the x-axis. But every single one of these functions is equal to 1 at 1 and is continuous. So it has to make this very rapid ascent at some point, right? It makes a very rapid ascent and has to go whoop and come up to 1. So it has this sort of weird behavior. And that sort of leads to this limit being weird, right? So here, let me, I have this link here. Let me share. So if any of you want to mess around with it, I've thrown that in the Zoom link or in the Zoom chat. And you can mess around with that thing. You can change your, change the N slider, right? You can make it bigger than 40 if you want. Okay. And, oh, why can't I share my other screen now? So we can kind of see that graphically, right? That sort of gives us an intuition for why this thing is converging. And you might say, okay, that's cool. So first let's show that it converges, but then let's think about like why this is obviously bad, right? Okay, so let's prove that it converges. And the easiest point is probably to just the point 1, right? So note that Fn of 1 is equal to 1 for all n. So certainly, we're going to have that the limit as n goes to infinity, Fn1 is equal to 1. And yeah, that agrees with this function here, right? It's 1 at 1, no problem. So now we need to show that, it kind of works for other points. Now, if you really, really want to, you can epsilon delta this, but I don't really think that's necessary. We know how to take limits at this point. If this were maybe earlier in the course, we'd worry about it. But I'd say, okay, so now let's take any other x naught. Any other point in 0, 1. So that if we take the limit as n goes to infinity of x naught to the power of n, right? Well, these are the terms of a geometric series. So like these certainly go to 0, right? In fact, this is like that we use this fact when we prove that a geometric series converged, right? So yeah, because x naught is between 0 and 1, if it were bigger than 1, it might be a different story, right? But because x naught is between 0 and 1, as we go to infinity, this number is going to become 0. Again, if you really want to go through and do an epsilon delta proof of that, but this isn't anything too scary, right? So this is equal to 0, and we're done. Actually, I guess, did I want to maybe all right, you know what? I kind of do want an epsilon delta just so I can show you the n dependence. So, all right. And if you're taking notes, just write this underneath it, right? So let's say n let epsilon greater than 0. Choose n such that, what do I want here? So I want x is, where did I do this proof? So that x is less. Well, wait, I'm going to choose the x to the n is less than epsilon. So x is less than epsilon over n, right? So, right, okay. Like that. Okay, so just as when you take higher powers of a number between 0 and 1, is this what I want? Hold on, I guess I really should just say x to the n is less than epsilon, right? Because I know that x is some number between 0 and 1, and so it's strictly less than 1. As I take higher and higher powers of it, it's going to get smaller. And so I can eventually choose an n sufficiently large such that x to the n is less than epsilon, right? And you can see like this is basically, we're done. So now if n is greater than or equal to n, then we're going to have x to the n is less than x, well, it's actually positive, so we can just get rid of the absolute values. X to the n is less than or equal to x to the power of n. And with this, non-strict, just because, 0, x could be 0. And then we're done. All right, so that's not too bad. Okay, and of course I could have written this as x is less than epsilon to the power of 1 over n as well, but maybe it's more instructive if I write it like this. Okay, and I went ahead and actually made a chart here so we can kind of see what's happening. And again, if you remember that diagram that I gave you, what you can imagine is that as x becomes closer and closer to, or as what do I want to say? As x gets closer to 1, we're going to have to go further and further into our sequence in order to ensure that this underlying thing happens. Right? Like if x is 0.99, yes, taking higher and higher powers of x is going to make that number shrink, but it doesn't shrink very quickly. Right? So as I take much, bigger values of x, and in particular, values of x that are closer and closer to 1, we're going to have to take bigger and bigger n's in order to make this happen for any fixed epsilon. So I actually made a little bit of a chart so that you can see this happen. So let's say if we fix, so note the dependency on n. So if, let's say we took epsilon to be 0.01, then, all right, so here's my chart. So let's say I'm going to set x, and then here's the n I'm going to choose. So 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, just for fun. And this is the n that you need such that x to the n is less than epsilon. Okay. And actually, you might say, well, okay, maybe we actually didn't choose a good bound, right? This is the minimal n such that this is true. And you might say, well, in the process of doing an epsilon delta proof, we're not guaranteed that we get the best one. In fact, in this case, this is the best one that we can do, right? This is the best n because we didn't do any sort of approximation anywhere, but more importantly, these functions are all strictly increasing. So you can actually determine the precise point when x enters that sort of epsilon band for a fixed x. All right, so what did we get here? So we got 2, I went and computed these, 2, 3, 4, 6, 7, 10, 13, and then it explodes, 21 and 44. Okay, so you can see here that there doesn't seem to be really this independence on n. You can imagine if I went to 0.95 and 0.99, that number n actually really quickly explodes. And you can check that yourself, right? Just go plug this, ask Wolfram Alpha to solve this. But in fact, it's even easier than that. What is it? Basically, because this function is strictly increasing, you actually just need to solve x to the n is equal to epsilon. And what do you get? You get n is equal to log epsilon over log x, right? So epsilon is fixed here at 0.01. Plug in x's that are bigger and bigger and bigger, closer and closer to 0.99. And you'll see like this number explodes, right? It's starting to get really, really big. So this is going to be a problem. It's precisely this fact, which gives us this pathological properties of this sequence, right? One of the things that should really bug us is that this sequence, everything here is really nice. The x to the power of n function, that thing's continuous, that thing's differentiable. Like it has all of these nice properties, but then I go and I compute the limit of this thing. And in its limit, I lose continuity, I lose differentiability. None of those properties are preserved under pointwise convergence, right? And that's a huge problem. That's something that we don't want. Okay, we could probably do another one here. Yeah, just for the sake of example, maybe let me just do another one really, really quickly. And again, this is one I think actually in this case, I might not do the epsilon definition. You can try it on your own if you want. So what function do I want here? Okay, so let Fn be the map from R to R. And it's going to take x to x squared e to the x over n, right? Show this converges to this function. And you can probably guess what it is. X maps to x squared, like so. Okay, and again, you can graph that thing. I'm trying to remember if I did or not. Did I graph this? No, that's a different one. Okay, we'll come back to that one later. So again, in this sort of thing, you can do this with an epsilon definition. This one's a little bit nasty if you want to do it with an epsilon definition, but there are a couple of arguments you can do to save your save your time, make life a little bit easier. But I don't think that's necessary. Let's just do it as a limit argument. So let's say note. So for some fixed x naught in R, note that if we take the limit as n goes to infinity of fn x naught, that's going to be the limit as n goes to infinity, x naught squared e to the x naught over n. Now I know this limit is going to exist, so I can actually use the limit laws. And the point here is that x naught is constant in this limit, right? What are we limiting? We're limiting over the index n, not over x, right? X naught is fixed in this question, so no problem, you can take it out. Like so. Okay. And then in this case, what I would do is I would say, okay, this thing definitely is, this limit here is equal to 1. And if you want to argue that, what you basically say is x naught over n, that's going to limit to 0 as n goes to infinity. That proof is trivial. E is continuous, right? And so basically that allows you to take the sequence inside, right? Do you remember? A function is continuous if and only if it preserves convergent sequences. So x naught to the n converges to 0. The function e to the x is continuous at 0. Therefore, if I compose that function e to the x with my sequence x naught over n, that thing must also converge, and it must converge to e to the 0. Right? And that is f of x naught. That's what we wanted. And in fact, for the epsilon delta definition, epsilon delta definition of this, I would do effectively the same thing. I would say x naught over n converges to 0. We know that. You don't need to prove that. And instead of trying to, do something with logs and log of epsilon, I would say, therefore, e to the x naught over n converges to e to the 0, which is 1. So I would do my epsilon n sort of definition there. I would get e to the x naught over n as close to 1 as I wanted, instead of getting x naught as close to n and then trying to filter it through all the other functions, right? Really leverage continuity, the fact that we know that continuous functions preserve convergent sequences, and do it from there, right? Otherwise, it's really gross if you need to be like, oh, okay, let x naught log or x naught over n be less than log epsilon or something so that the e's and the logs cancel out. That's a whole mess. Don't worry about that. Really leverage continuity of your function, right? So that's how I do that. But again, here from a limit perspective, we don't have to do that. We know how these things work. So that's not too bad. Okay. All right. So as we've seen already, one, pointwise convergence does not preserve continuity. So notes. Number 1. Pointwise convergence does not preserve continuity. Okay, this is an issue. And the example for this was our functions x to the n, right? This converged to this function, 0 if x does not equal 1, 1 if x equals 1, right? So that's an issue, but it's worse than that. 2, pointwise convergence does not preserve boundedness. So, because you might say, at least in this previous example that we did of x to the power of n, those functions are all bounded, at least their limit is also bounded. Well, it turns out that doesn't need to be true. Okay, and the example for this is the following. So let's take the open interval 0, 1, and let's map x to, what did I do here? It's just very cleverly written. Which functions I want to use. Right. N squared. Squared x squared. Okay, so I've deliberately sort of obfuscated what this function is actually doing by having done some algebra ahead of time, but I'll show you what it is in a second. Show that this function converges to 1 over x squared. Okay, so this is what we want to do. N squared over n squared, x squared plus 1, and that's going to converge to 1 over x squared. And again, if you look at this thing and you say, what happens when I take n goes to infinity? It's sort of that classic trick where, again, assuming that x is, a fixed constant, and we're taking n going to infinity, I've shown you the trick for evaluating these limits. Basically, you look at the coefficient of the n squared, because that's the highest order term. You look at the coefficient of x squared in both the numerator and the denominator. In this case, in the numerator, it's 1. In the denominator, it's x squared. So this thing's going to converge to x squared, or 1 over x squared. And if we set up here, I've got the Desmos thing for this again. Okay, so we've got this. And here, let's see. Hopefully you can see it. You definitely, once I start moving the index here, you will see this function show up here. Let me move it a little bit. There we go, so you can see it. So here is our limiting sequence. This, what color is that? Green or whatever. And then we've got our 1 over x squared here in blue. And as I move that thing, it certainly seems to be getting closer, right? So it is converging. Now we know 1 over x squared is not bounded, right? This thing has a vertical asymptote at 0, right? The blue thing is getting infinitely big at 0. But each of these green things definitely exists at 0, right? In fact, if you plugged x equals 0 into this equation, what would you get? You get n squared over 1. So it just, at 0, it's totally defined. And that'll be true for any n, right? So you just get 16 here. Next one, you get 25. Then you get 36. So yeah, definitely bounded, totally defined at 0. But as you take a limit to infinity, well, it becomes unbounded, right? So hopefully we believe this just by looking at the graph. Here, let me post this one in the Zoom chat in case you want to mess with this yourself. So hopefully you believe this. Obviously we're going to prove it in a second, but here's our issue. We have a limit of a bounded or a pointwise convergent sequence of bounded functions, which converges to something which is not bounded. So that's our issue there. Okay, so let's prove that real quick. And again, basically, if you really want to epsilon this, you can, but I really don't think it's necessary. So solution, let's say fix some x naught in 0, 1. So that the limit as n goes to infinity, fn x naught. Again, x naught, just a constant here, right? It's n that's limiting. So we get n squared, x squared plus 1. Again, typical sort of trick here. Multiply top and bottom by 1 over n squared. So that's going to give me 1 over x squared plus 1 over n squared. That thing right there, right? This thing converges to 0. So I get 1 over x squared like that. And I'm done. Right? Because that's or x naught. I guess I dropped my x naughts everywhere. I should put those back in. And then maybe say, oh, and that is in fact f of x naught. Like so. Okay, so certainly each fn is bounded. Note each Fn is bounded, but F is not. So pointwise convergence doesn't preserve boundedness either. And it basically seems like nothing we want to be preserved is preserved, right? Pointwise convergence is the most naive. It should be the first thing that we try, but it's the most naive. It's sort of the most limiting for that reason. So we want some sort of stronger notion of convergence, at least something that's guaranteed that we can preserve some properties, right? I'd like to know that if I take a limit of continuous things, that the resulting thing, if it converges, then the resulting thing has to also be continuous, or that if I take a limit of bounded things, that the resulting thing has to be bounded, right? That would be nice. But in order to do that, we have to strengthen our definition of convergence. And this is where we really are going to diverge from the study of sequences and series of real numbers, is that we're going to have multiple different notions of convergence. And like I said, as you take more and more analysis, you even learn more and more and more and more definitions of what it means for sequences of functions to converge. So this leads us to wanting a better definition. And so here's our better definition. So a sequence, of functions is said to converge uniformly to F if, and now we are going to have to kind of write out the epsilon n definition, because the placement of the quantifiers is the important thing. If for every epsilon greater than 0, there exists an n in n, such that for all x and I, and for all little n bigger than or equal to big N, this is true. Okay, and again, if we look at this, no, that's not the one I want. If we look at this, so in the pointwise convergence definition, that's at the very beginning, or it could occur after the epsilon. It doesn't matter, because if your quantifiers are the same, you can mix them up, right? But the point is, it occurs here. It occurs after the existential quantifier in capital N, and in pointwise convergence, it occurs before. And we know that when you mix universal and existential quantifiers, it changes the dependence. So importantly here, this n has to hold down for all x's. So let's say note, this value of n only depends on epsilon. On epsilon, not on x, as in pointwise convergence. Okay, so that's kind of the critical point here. The n in pointwise convergence can depend on your point, right? What point you're using. But the reason why we use the word uniform here is that, right, uniform, what does that mean? It means sort of like it's the same throughout, right? That's what uniform means. And so we're going to converge uniformly if the same value, if a single value of n works for all of our points x. And that's very similar to uniform continuity, right? When we were talking about continuity, we knew that, a function is continuous on a set if for every epsilon you can find a delta, but that delta is generally allowed to depend on what point you're looking at, right? What x you're working on. Here, we're saying that, and you were uniformly continuous if you could find a delta which worked for all your points, right? Which worked for every x. Same sort of story here, right? It's a different notion now, because now we're looking at sequences instead. We're saying that there's a single value of n which works for everything. Okay, so that's our idea there. Am I going to do a uniform proof? Maybe let me do a uniform continuity example really, really quickly. And let's see. Let it to blah, 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 blah. Sure. Here, let me do a really quick and dirty example, just so you have something. So let's take a look at these functions. So let's say define or show that. And I think we can just do R. Okay, so it's n squared plus x squared converges to this function, which is just the zero function. It's sort of boring, but that's why it's a relatively simple example. Uniformly. Sure. Okay, and so again, you can plug this into Desmos. I don't have this one ready, but it's relatively straightforward to plug into Desmos. Even just don't even worry about the slider. Plug in 1 over n squared plus x squared and then hit enter. Desmos will be like, hey, did you want a slider? And we'll give you one. And then you can see what this thing looks like. And yeah, I mean, it's kind of boring in some sense. Again, we expect this to be true, but as n goes to infinity, the n squared here is actually sort of the dominating thing, right? It doesn't really even matter what x squared is sort of doing. I mean, obviously for a fixed x, this function is going to go to 0 as you go to plus or minus infinity as well, but you sort of expect it to have a little bit of a hump in between, right? But think about what that hump is. The maximum of this function looks like it's probably going to occur when x is equal to 0, right? And at x equals 0, what is its peak going to be? It's going to be 1 over n squared. And so as you let n go off to infinity, that little peak that you have, right? Your function sort of looks almost bell curvy. That little peak that you have is going to start to squish down. So it looks like this function is converging to 0, but it's actually going to converge to 0 uniformly. Okay. Now you have to do these ones. Unlike Pointwise, where we could kind of get away with just throwing a limit in, with uniform, you really have to epsilon it because, you know, again, just doing a limit, when you do a limit like we did before, where you just write lim as n goes to infinity, you're hiding where the n is, right? But you can't do that with uniform continuity. So in these cases, you really kind of have to go to the epsilon definition. So let's let epsilon greater than 0 be given. And choose n such that 1 over n squared is less than epsilon. Okay, and let me highlight this. There's no x's here, right? No dependence on x or x naught. Okay, and let me scroll up really, really quickly to when we were doing the x to the power of n example, just so that we can see in those two proofs, you know, the difference between picking our n. So if I scroll up really, really quick here, let me highlight this. Right? Or again, we could have said here, you know, choose n to be log epsilon over log x, right? We could have written that instead. X shows up, right? In the definition of capital N there, that n depends on the value of x. And when I choose different values of x, I'm going to get different values of n. So there is an x here in my dependency for capital N. That's going to be a big hint that this actually isn't uniformly convergent. Okay. And again, you might say, well, that actually doesn't prove that it's not uniformly convergent. That just maybe proves that we were sloppy when we chose our n. It's not, right? But here, there's no x's, right? I just said let 1 over n squared be less than epsilon. Boom, this is independent of x. So this is going to work for every x. So let epsilon greater than 0 be given. Choose n such that this is true. Now, if n is greater than big N, we've got f n of x minus f of x. All right, so what is this? Let's plug this in. So we get 1 over n squared plus x squared minus 0. Everything's positive. So that's really just 1 over n squared plus x squared. That's less than or equal to 1 over n squared. And voila. right? So again, sort of like an easier one because we didn't have to do any really nasty, complicated manipulations. But again, you can see this works for all x, right? Because effectively, I just threw the x away. I was just like, go away. And this is effectively what I said, that this function, its maximum does occur at 0, right? When x is equal to 0, and there it takes on the value 1 over n squared. So this function is always less than or equal to 1 over n squared. And of course, you can make that thing go to 0 without much problem, right? So you can do that. Okay, so that is that. We'll go on our little break here. What I'd recommend as a little bit of an exercise, if you want to try it, is so one, prove that x to the n is not uniformly continuous, right? So that's not too hard of a proof. So check that it's not uniformly continuous. And then if you want, right, the whole reason why I brought up, where is it? These notes right here in green in the middle of the screen, is that uniform continuity probably, or uniform convergence, sorry, is going to preserve these things, right? A uniformly convergent sequence of continuous functions is going to be continuous, and a uniformly convergent sequence of bounded functions is going to be bounded. Neither of those proofs is terribly hard, but the boundedness proof is easier. Okay, so you can totally try that one on the break if you want to get a feel for this. Prove that if you've got a sequence of bounded functions that converges uniformly, then the limit is also bounded. Okay, continuity, a little bit trickier, but the bounded oneness isn't too bad. So try that, and we'll come back. So let's do 10 minutes here. It's looking to be about, it's like 10:02, 10:03 by my watch. So we'll come back at 10:13 or so, and then we're just going to, prove a glut of theorems about uniform continuity. Or uniform convergence, sorry. And all the things that it preserves. And then unfortunately, there are some things it doesn't preserve either. So we're gonna have to deal with that. Okay, so 10 minutes, 10:13 local time, and we'll pick up from there. See you soon. All righty, so we'll pick back up here. And I guess, what I should give you, it occurs to me I didn't draw you the picture of sort of what's going on with uniform continuity. And it's not too hard to visualize what's happening. So again, if we sort of look at this definition for every epsilon, there exists an n such that for every x, blah, 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 blah. And if you take this condition here, that sort of final condition, fnx minus fx. So if you take this condition here and say, well, this has to be true for all x, then what this means is that basically your functions have to live in this little epsilon band, but the epsilon band follows the limiting function. So let me draw that so you can see what I mean. Oops. So, to visualize uniform convergence, and I think this will help. I think this really does help. So here is, that's not a good x-axis. Let's draw it quicker. So here's my x-axis, and then maybe here is my limiting function. Right, so here's f. And then let's say I've got some sort of epsilon band around it. And again, though, the epsilon band now, instead of just, when we do limits of real numbers, that epsilon band is sort of just, it's a straight line, right? But now what's going to happen is that epsilon's actually going to follow the contours of the function itself. So this is the big difference about, what's kind of happening with uniform continuity. I guess that should go down here. And then something like this. Okay, so this thing up here, this is going to be f plus epsilon. This thing down here is f minus epsilon. So you're just taking your function, you're going to translate it up by epsilon, you're going to translate it down by epsilon. And this creates for you this sort of epsilon band, but it follows your function. And what you're saying is if you go far enough into the sequence of functions, then every function must live inside of this little epsilon tube, right? Maybe we'll call it an epsilon tube instead of an epsilon band. Epsilon band being sort of straight lines and epsilon tube being this sort of thing that follows the function. it says if you go far enough in, every function, it doesn't matter what it does and how much sort of like crazy it oscillates, it must stay all, oops, oh, that's too far. Damn it, I drew this as one line, so it's gonna erase everything. You know, but whatever, it doesn't matter what we draw. So let's not screw that up this time. Eventually, all of the functions, when you look at their graphs, all of the functions live in that tube, right? So if you go far enough into the sequence of functions, all the functions live in this little epsilon tube, right? They all stay in there. And it doesn't matter, they could oscillate really quickly or jump sort of all around the place, but eventually, all but finitely many of the functions live inside of that little epsilon band. And so what you can see here is that as you squeeze that epsilon band down, right? And again, you're forcing the functions to live inside of there. They are going to have to converge to F, but they converge to F in a much nicer way than just pointwise convergence, right? So maybe let me just state this as an exercise, but then I'll draw it as well. So exercise. Showed that from our previous example, this does not converge uniformly. And it's sort of easy to see why, and the picture will help you understand the proof as well. So if I were to draw that example, right, and let's say here's one here, and then my limiting function, I should have used a different color other than yellow up there for the limiting function, whatever. So here is my limiting function, right? It's just constantly sort of 0. And then it's 1. Let's say that's 1 up here. And if you draw an epsilon band around this thing, right? So your epsilon band now, or your epsilon tube in this case is pretty nice. It is basically an epsilon band. Right, and then technically there's sort of like this infinitesimal little epsilon tube around here. But if you draw a function, x to the power of n, it doesn't matter how big your n is, it's going to leave this tube, right? Because it might look something like that, right? So here's maybe x to the like 50 or something. But of course, it doesn't matter what that is. It's always going to leave that tube, right? Because eventually it has to go whoop and sort of rail upwards. And in doing that, as long as you choose a small enough epsilon, right? As long as you don't choose epsilon as 100 or something, so it completely captures the 0, 1 range. If you choose an epsilon sufficiently small, you can guarantee that you can always find an xn that's going to leave this tube, right? And we said uniform continuity, no, all the functions eventually have to stay in the tube. And no, here definitely clearly all the functions eventually leave the tube, right? So this can't be uniform. The way you're going to prove this is just exactly like this, right? Show that the function leaves the tube. And that's relatively straightforward to do, right? Like epsilon be a quarter, and show that there's always, you know, for any n, you can find a point that's equal to a half, right? And then you leave the epsilon tube and you're broken. So this one, like I said, this exercise is fairly straightforward to do, but is worth doing. You might sort of, it's the sort of thing that might fluster you for like 5 to 10 minutes, but once you think about it a little bit more and write it down, it shouldn't be, you know, it shouldn't be terrible. You should be able to put it together without too much trouble. Now, this sort of smushing together that we don't get here, and same sort of thing as well, right? Like if you think about the unbounded example, right? When we had these sequences of bounded functions whose pointwise limit was unbounded, that's not going to be uniform either. And again, I would just recommend that you draw the epsilon band and you'll see that this is true. Because yeah, if the function is unbounded, your epsilon tube sort of shoots off to infinity as well. And there's no function that will always also shoot up to infinity, right? All those other functions are bounded and your limiting function is unbounded, so they can't stay in your epsilon tube. And as a result, they're going to leave, and so you're not uniformly continuous or uniformly convergent. But this uniform convergence is what's going to give us continuity and boundedness. And like I said, boundedness is a little bit easier to see just because, hey, listen, if I tell you, right, like if I give you this picture here at the top of the screen and I tell you that yellow function is bounded, and then it's also has to be in this epsilon tube of your limiting function. How could your limiting function not be bounded, right? Like the other function can get at most epsilon away from your function, right? The yellow function. So it can get at most epsilon away from your blue function, f, and it is itself bounded. So the worst that could happen to f is that it's epsilon plus whatever the bound for the yellow thing is away. Does that make sense? Right? Like if you have to live within epsilon of the blue thing, and then the yellow thing is also bounded, well, that's going to force the blue thing to be bounded as well, right? So that's sort of like the nice thing that we get. Continuity is a little bit harder to see. It doesn't have as nice a geometric picture, but it's sort of like algebraically not too difficult. But let's run through that. Actually, was there another example I wanted to do? I don't think so. Yeah, I think that's okay. So let's just start proving things. So theorem, and again, we're just going to start with the easier one. So theorem. So if Fn is a sequence, and again, here, right, I'm being lazy because I'm not saying what the domain is. But if Fn is a sequence of bounded functions, and here the important thing is bounded, which converges uniformly to f, then f is bounded as well. Okay, so this is telling me that unlike pointwise convergence, which did not preserve boundedness in its limit, uniform convergence is going to. Okay, so uniform limit of bounded functions is bounded. That's sort of maybe a more pithy way of saying this, right? A uniform limit of bounded functions is bounded. That's kind of how a mathematician would say it, I think. And the proof's going to go pretty much exactly how I do it. Now, with these sorts of proofs, let me sort of give you the rough work. Okay, I want to show you how you do these sorts of proofs. So with these sorts of proofs, you really want to work backwards. And again, just think about what you have access to. So this isn't going to be as big a deal in this problem, but it is going to be a little bit more when we do continuity. And I'll show you a bit more what I mean there. So I want to make some sort of statement about f. I want to show that f is bounded. So as my rough work, right, what I'm going to do is I'm just going to start with this thing. And that's what I'm trying to show, that's less than a number, right? And I say, okay, well, what do I know? Well, I know that Fn converges to F, and I know it does it uniformly. So again, I need the Fn's to show up. So let's just add them sort of artificially. Like this, and then use the triangle inequality, right? You're like, all right, this is really good because now this thing, that's bounded, right? And I have control over this. So great, I should be able to create a bound, right? I can make Fn's get as close to f of x as I want. In particular, I get to choose the epsilon, right? And I might choose epsilon to be 1 or a half or whatever you want it to be. And then I know that each of the Fn's is bounded. And you might say, well, the right-hand side also depends on n though, right? Because the bound could actually be different for every function. But you say that doesn't matter. I just need to show there's some n that, there's some bound that works. And so if I'm clever and I sort of fix the right n, then I will get a bound here. Okay, so in terms of the proof proper, so what I'd say is, let epsilon be 1. And choose, n so that our definition of uniform continuity holds. But in particular, right, the fact that I've used n greater than or equal to capital N, or you could use little, capital N plus 1 if you want, it doesn't matter. That's going to be the n that I'm going to use. Okay, so in particular, and of course, you could do this with any little n bigger than capital N, but there's something appealing about using capital N. All right, so that's what I mean by this, right? You'll notice that here when I wrote this down, I didn't write down a little n. I'm using capital N. I'm using that particular value of n. And again, you could use capital N plus 1 if you really want to, or something along those lines. It doesn't matter. And right, again, I know that, I guess this is a strict inequality here, but I know that first thing is less than 1, pretty much by definition, and I get this. And then again, a capital F, like f of capital N is bounded. Moreover, there exists some m greater than 0 such that f and, nope, capital N for all x in whatever the domain is. So that means f of x. Right, i.e. f is bounded. Okay, and again, you know, we should think about this a little bit, because I used a particular sort of value of n here. But again, that sort of that capital N has to be capable of changing. Like, think about this for a little bit. Convince yourself that it's not enough for one function to be bounded. Well, I guess it actually is. If you're uniformly convergent, it is actually enough for just one of the functions, or like a sufficiently nearby function to be bounded. But yeah, just be careful when you use that, because I only needed that it worked for capital N, and that capital N corresponded to epsilon being equal to 1. But that being said, like, again, the moment one of those functions is bounded and you have uniform convergence, it effectively forces all the other ones to be bounded as well, right? So we're not super worried about it. But this is the sort of thing that can't happen with pointwise convergence, right? Precisely, again, because I would really, actually, let's stare at this for a second and think about where I really used uniform convergence. Because I can't say that there's one value of n, which just makes this less than 1, right? Again, I'd sort of need to change the value of capital N here. If I only had pointwise convergence, for every x, I need to choose a different n. And if I have to choose a different n, well, generally, these things are bounded. You can't say that they're all bounded by the same capital M, right? We don't know that. So they're each bounded by a different number. And so the critical thing here was that I was able to use just one n in order to do this, so that I could bound this just by one of these things, right? Otherwise, this wouldn't have worked. Does that kind of make sense? Because in our other example, remember when we showed the pointwise convergent limit of these bounded things, which converge to an unbounded things, those are each bounded, but they're bounded by a different number, right? And that the number that bounds each of those functions, n squared over n squared x squared plus 1, these were all bounded, but they were bounded by increasingly bigger numbers, right? So the critical point here was that I could use a single n in order to do my bounding, instead of having to use different n's for different, for every different point, because that just wouldn't have worked. But again, even just from like a geometric viewpoint, you can see the sort of like epsilon tube squishing argument is going to force your boundedness anyway, right? But this is why this proof wouldn't work if we had done it pointwise, because we just wouldn't have been able to use a single n. Okay, makes sense? And I guess it's worth saying here, again, I really want to emphasize, in general, this bound here, this capital M, is going to change for every single one of your functions, right? If it's the same bound, that's a different definition, right? If you have a sequence of functions and they're all less than or equal to m for some m, then we would say that that sequence is uniformly bounded, right? For the exact same reason. They're each bounded separately, but they're not necessarily bounded by the same thing. If they are all bounded by the same thing, then they're uniformly bounded, right? That every single one of them is bounded by the same thing. So that is actually the definition of uniformly bounded. I don't think it's going to come up. I don't recall. It's the sort of thing that you use if you go take 337. We don't even talk about this in 257, even though it is sort of an interesting thing. uniform boundedness is important. It's, if I recall correctly, I think it shows up in our Zela-Ascoli. So when you want to show compactness on like function spaces, I think you use uniform boundedness. So it actually does show up there. It is a sort of an interesting and important topological property, but we're not worried about it in this class. We're not going to do our Zela-Ascoli. Okay. So there's the proof for boundedness. Great. And in fact, this automatically proves that that previous example we did couldn't have converged to pointwise, right? Because otherwise, or sorry, couldn't have converged uniformly, because if it did, its limiting function would have had to have been bounded, and it wasn't. Next theorem is going to be the continuity one. So it's the exact same statement, only continuity is now preserved, right? So if Fn is a sequence of continuous functions, that converges uniformly to F, then F is continuous. Okay, and math saying of this would be that the uniform limit of continuous sequence, the uniform limit of continuous functions is continuous, right? That's how a mathematician would internalize this result. Uniform limit of continuous functions is continuous. Okay, this one's a bit trickier. It doesn't have an as clear a geometric picture. This is the sort of thing that for me, I really would just do by algebra. Okay, and anytime you're trying to do things with sequences, it's usually sort of the same sort of trick, sequences of functions, which is again, just sort of say like, what do I know about and how do I sort of synthesize this and put this together? So let me show you what I mean by my rough work here. And I'm not going to write it out in like crazy detail, which you can do if you want. Okay, so I want to show F is continuous, right? Again, you sort of write out what that means. So you want to say, okay, so I want to show for every epsilon greater than 0, there exists delta, such that if x minus c is less than delta, f of x minus f of c is less than epsilon. Okay. So basically, we need to sort of start with this thing, right? Even when we were doing our rough work of proving functions were continuous, that's the place we would start. So I need to do something about f of x minus f of c. All right, what do I know? So there's two things that I know. Actually, maybe let me write them out. So what do we know? We know 1, Fn converges to F uniformly. And 2, Fn are continuous. So that suggests that we probably need, oh, that didn't work. So we need the Fn's to occur in this expression. So let's make them show up. Hopefully you'll forgive me if I just go straight to the triangle inequality. Let's just do x for now. Like that. And you say, okay, that's not terrible. This is some sort of uniform. This is some sort of uniform or convergence, right? So with uniform convergence, I can control that. The other thing, though, I don't know what to do. Right? I look at Fnx and I look at f of c and I say, okay, well, this is kind of an issue here because it's like I'm mixing things, right? I've got this convergence of n to Fn to f, but I also have x converging to c. So the fix to this is to throw in another, Fn, and let's throw in Fn of c now. Does that kind of make sense? Do you see like that this is a mixing of terms? I've got both Fn is converging to f and x is converging to c. I can't do both of those things at the same time. I don't know how to deal with it. But I can deal with it by throwing in an additional thing. Okay, so I'm going to keep the first thing the same. And now I'm going to change this part here. Maybe even let me draw this in a different give this a different color so you know which part I'm changing here. So let me draw that in yellow. And then, so this part is going to be fnx minus fnc plus fnc minus f of c. Right? And you just keep unraveling. Again, you don't want to do multiple things simultaneously, right? Things that you know about simultaneously. So you're just going to keep adding and subtracting terms until you've kind of pulled out each of those things separately. Once again, we get uniform convergence here, and now we also get it here. So here's a uniform convergence. This is now also uniform convergence, right? Because they're both at C. We've got FNC in the rightmost term. We've got FNC minus f of c. Evaluation is at the same point. So now I'm only looking at, what happens as n changes. And this is why uniform convergence is going to be important, right? Because I'm going to be able to use a single n to bound both of those things simultaneously. And the middle thing is just straight up continuity. Right? So this is like property 1. This is property 2 of what we know, and this is property 1. And where uniform convergence is going to be important is that, I'm going to do some sort of epsilon over 3 proof, and I'm going to be able to use the same n to epsilon over 3 the first term and to epsilon over 3 the third term simultaneously. Okay, so in terms of your rough work, that's what you keep doing. You just, here, you know what? Let me use little n everywhere because I don't necessarily know whether I'm going to use big N, so maybe just change them all to little n's. But just keep adding and subtracting terms until you're only sort of until you've broken it up into something that you can bound, right? Each of those things separately. So now if we do the proof proper, again, like I said, it's sort of an epsilon over 3 proof. So the proper proof, right, is we're going to say let epsilon greater than 0 be given. And now we have to be careful about the order in which we choose delta and n, right? Because we kind of have to make both of those choices. Now, the definition of continuity, because I'm trying to show just f is continuous, there's no n's involved here, right? So really, I should try and, like I said, you have to be careful about how you choose your delta and the order that you choose your n in, right? Because I can't now just be like, let's choose delta. How am I going to choose delta? I want to do it so that fn is continuous, right? But in order to do that, I have to have an n first. So I need to make sure I pick my n first. So and choose n in n such that n greater than or equal to big N fnx minus f of x less than epsilon over 3 for all x. All right, so I've chosen my n first. This is my first and my third terms, right? Already check, check. I've done my epsilon over 3s on the first and the third term. So now I just need to epsilon over 3 my middle term, and I need to pick a delta, but that's fine because this is where my delta is going to come from, right? So now choose delta greater than 0 such that x minus c less than delta implies, and again, you have to use a fixed n for this so that, Nicole, you kind of see that I was kind of thinking ahead. Here's where I'm going to actually use my capital N. And again, you could use capital N plus 1, you could use 2n, whatever you want. Just make sure you choose something bigger than or equal to n. And again, I can do that because I know all of my f's are continuous, right? So now that I've got this, epsilon over 3. So now if x minus c is less than delta, then we've got f of x minus f of c less than or equal to fx f. Now it's capital N plus fn of x minus fn of c, fn of c minus f of c. Each of these is an epsilon over 3. And there's 3 of them. And again, if it's 3 epsilon or epsilon over 3, who cares? It doesn't make a difference. And there we go. I'm done. Okay. And there's something nice here too, in some sense, that you can see almost immediately, you're probably not going to be uniformly continuous. Well, are we going to be uniformly continuous? No, I don't think there's any reason to suspect that would be true. But here again, we can see the importance of how delta is going to change depending on what our epsilon is, right? Because we know delta is allowed to depend on epsilon. And it's a little bit tricky. It doesn't quite look in this example as though delta depends on epsilon, but it does. And the reason for that is delta depends on capital N, and capital N depends on epsilon, right? Do you see that? So delta here, how did we choose delta? Well, we chose delta so that it works for F capital N, right? We chose the same delta that works for F capital N. But how did I choose F capital N? Well, I chose capital N to make sure that I was far enough into the sequence to be always within epsilon over 3 of little f, right? So this is a little bit more convoluted than how we normally see delta depend on epsilon, because we kind of have to, traverse through capital N first, but nonetheless, we still have delta depending on epsilon here, right? As we would expect, right? Because generally delta should depend on epsilon. The only kind of time it doesn't is if you've got a constant function or a linear function, right? So we expect that to be true. It's just not as clear in this case, but if we think about it and filter it through, it's still there. And if you look at my proper proof, it's still not that big, right? Like this isn't a crazy long proof. In fact, most of this is just me doing rough work, so kind of showing you how you would reason through this sort of thing. But yeah, it's not, it's not too terrible at all. I guess I want to do one more positive proof. Are there any questions about this before I move on? Like I said, I don't really have a nice sort of geometric picture for this other than the fact that algebraically it just works. That's sort of unfortunately what happens when you just keep adding and subtracting terms over and over again, right? There might be a nice one, but I'd probably have to think about it a little bit more. There isn't an immediately obvious one. Okay, all right, so the next thing, we're going to see something a little bit weird. The next thing is that uniform continuity also preserves integrals or antiderivatives. Okay, so let me just get the theorem statement here. So suppose Fn is a sequence. I should. This one I actually kind of do want to explicitly state what the domain is, because I just want to, when I define the antiderivative, want to be able to use that lower bound of integration. So in this case, let's actually explicitly define it. Suppose Fn is a sequence of integrable functions which converges uniformly to f. And again, right, it's got to have the same domain and everything. If we define capital Fn in exactly, the way that you would expect it to be. I guess if I say what x is, I have to include it. Okay, so if I define capital Fn to be, the antiderivative of little fn in the usual sense, and f is, or I should say this. Yeah, to actually, oh shoot. You know what? Here, let me just move this out of the way real quick. No, what are you doing? Okay. Then f is integrable. Moreover, now let's move this thing back over here. All right, you know what? I'm giving up on you, Windows. You're not doing what I want you to do. And F. Right? I'm blaming my tools because it can't possibly be my fault that I'm sucking. Okay, so if Fn is the antiderivative of little fn and f is an antiderivative, or is, an antiderivative of little f, then Fn actually converges uniformly to f. Okay, and let me just make sure. Do I cheat at all here? I guess I do, because in my proof, I don't actually have that I'm proving that f is integrable. Let me just double check something here, because I feel like I've cheated a little bit. Because I think in my original set of notes, I didn't actually prove that f was integrable. Oh, I don't. Okay, actually, I'm a little bit hesitant to prove this then. I kind of assume that f is integrable. Let me think. Must this obviously be true? Is the uniform... So in the statement, in the theorem statement in my book, I have that f is integrable to begin with. I don't prove it's integrable. So let me try and think about whether the limit is actually integrable. Does it have to be? I'm gonna have to, yeah, that one's not as clear to me. All right, so here's what we're gonna do. Everyone do this and I'll come back with a better answer next time. So here, I'm actually not 100% certain that this part of the theorem is true. So what I'm going to do is I'm going to do the proof here under the assumption that this function is integrable first, and then let me think about it. And then on Thursday, I'll tell you whether or not that result is true. Okay, so I'm going to assume that f is integrable because I feel like it should be true, but it occurs to me that my proof doesn't actually do this. So assume that f is integrable. If we can prove it, we'll do it on Thursday. It does not seem to work when f is not integrable. If we take fn to be f plus 1 over n, what are you saying? So are you giving me an example of a uniformly convergent sequence which converges to something which is not integrable? So an integrable uniformly convergent sequence with non-integrable limit? Oh, wait. Yeah, you're saying that none of the fn's are integrable, like as part of your assumption? Because I mean, like, for sure, we have to take the fn to be integrable in this theorem. The only thing I'm wondering is, can an integrable and uniformly convergent limit converge to something which is non-integrable? Because something we're going to learn is very easy for a uniformly convergent limit to be non-differentiable, even if the original functions are differentiable. But integration is much smoother. It's a much nicer operation. So I feel as though it should be, but I can't immediately come up with a counterexample because our classic counterexamples of non-integrable functions are sort of like the Dirichlet function, right? And so if we want something which converges to that uniformly, we're going to be probably not integrable to begin with, right? So I don't see an obvious counterexample where the FNs are all integrable to begin with. So we definitely have to start with the assumption that the FNs are all integrable, right? For this theorem to be true. It's a question of whether or not their limit has to be integrable as well. So like I said, let's do the proof very quickly here, where we assume that F is integrable, because this proof is surprisingly straightforward. And then I'll think about whether or not the limit has to be integrable, because I can't think of an obvious counterexample, but I can't think of an immediate proof either. So I'm going to have to think about it a bit more. But Alexander, let me know if I didn't understand what you were saying there. But I think what you're saying is that you assume that the FNs weren't integrable to begin with, but that doesn't necessarily, like, that's not really in the context of this theorem, right? Like, we're trying to say FNs are integrable for sure to start with. That one's immutable. What can we say about it? Right, okay, sure. Yeah, my question here is the blue thing, right? Just does the limit have to be integrable? So, okay, so again, let's sort of rough work this. So let's say Fn has to converge. Let's basically just prove now. So we're assuming that little f is integrable. Let's prove that the capital Fn's have to converge to capital F. And let's show that that has to happen uniformly, right? So we'll revisit integrability. I'm going to spell that wrong. Integrability later. All right, so let's show just convergence. So let's show that Fn converges to F uniformly. Okay, so again, just sort of rough work, right? What do we want to look at? So we want to look at Fnx minus f of x, right? Okay, what is that? So that's the integral from a to x Fn minus the integral from a to x f. And of course, we can combine that, right? And again, hopefully you see, even, I think this is the sort of thing that looks scary, but the moment you write it down, you're like, oh yeah, okay, everything comes together. Right? Now we know subadditivity of the integral. I can put that absolute value inside at the cost of a less than or equal to, but that's not a big price to pay because, you know, we kind of want to do some bounding arguments anyway here. And well, that's a good thing, right? Because I can control that thing. Right? By uniform convergence of the Fn's to little f. So I can make this thing be fixed. And if I fix this in sort of like a clever way, and you might need to play around a bit with the number that you want to work, but if you fix this in a nice way, you're done. You can easily make this less than epsilon. So let me show you. So let's do the proper proof now. So let's let epsilon greater than 0 be given. And the clever thing, in order to sort of make this work out, and there's a couple of things you could have chosen, but choose n in n so that if we're bigger than big N, we get Fn x minus fx is less than. So I'm just going to throw this b minus a term in here. Okay, and you'll see why that happens in a second. For all x. Okay, so now by my rough work, so thus, if n is greater than or equal to n, so we're going to use the same capital N here. And I'm not going to repeat all these steps because we did it in the rough work. So I'm just kind of going to go right to the end here. So we get the absolute value of Fn minus f. And again, I need uniform continuity here in order to be able to bound this for every single x simultaneously, right? This would be really, really hard if I had to do this for every individual x, because of course the integral, is interested in the function in its entirety, or at least on the interval a to x. So I need to be able to do this for all of the x's simultaneously. And if I put this in, I'm now going to get epsilon over b minus a, or maybe here, let me put that inside the integral. It doesn't really matter. Right? And that's a constant. So when I integrate this, I'm going to get x minus a divided by b minus a times epsilon. And this number here is less than 1. Right? I guess we should say less than or equal to 1 because x could be equal to b. But that number is less than or equal to 1, right? Just it has to be. X is less than b, or less than or equal to b. So that number is less than 1. So this whole thing is less than epsilon. And we're done. Okay, just like that. So again, surprisingly, not that difficult. Now, the thing I want you to think about is how terrible. So this is great with integration, but I think the thing that's kind of surprising is that uniform convergence does not respect differentiability. So we've seen it does respect continuity, but it does not respect differentiability. And this is actually relatively easy to see, right? Basically, if you think about what could happen, you could take things that are sort of like this and are sort of becoming more and more jaggedy until eventually they actually limit to something with a cusp here, right? That's the sort of thing that could happen. And uniform convergence doesn't preclude this from happening, right? It doesn't say that can't happen. Sort of if you want an explicit example, we'll cover this more on Thursday, but a more explicit example, so maybe exercise, show differentiability is not preserved. Is not preserved. And here's a really easy example. Take something like this. And it doesn't have to be 1 over n squared, but let's be consistent with the squaring. Hopefully you see this thing will converge to the absolute value of x, right? As 1 over n squared vanishes, this will converge to the square root of x squared. That's the absolute value of x, which is definitely not differentiable. Each of these functions is also definitely differentiable, right? Because you don't get that sort of issue with the cusp. And then moreover, they are definitely also uniformly convergent. And of course, that's the thing you're actually going to have to prove. It's definitely pointwise convergent, but not necessarily uniformly. But in this case, it is. And that's not too tough to prove. So this is an example of a function which is everywhere differentiable, which converges to something which fails to be differentiable, in particular at 0. But the problem is actually much worse. So in this case, we have differentiable things which converge to something which is not differentiable. What if the functions converge to something which is differentiable? You know what I mean? Well, it turns out, unlike the previous example, the derivatives themselves do not then have to converge, even pointwise. Okay, so the situation is actually worse. So if Fn converges to F uniformly with Fn and F differentiable, we cannot guarantee that Fn prime converges to F, even pointwise, let alone uniformly. Okay, so Fn could converge to F. Everything could make sense so that I can differentiate things, and we might not have that Fn prime converges to F prime. Or sorry, F prime. Okay, we can't guarantee that even that is true. And I guess I've sort of been using this implicitly without explicitly stating, but hopefully everyone's okay with the fact that uniform convergence implies pointwise convergence, right? Like if you're uniformly convergent, you are pointwise convergent, because if there's one n that works for every single x, then certainly your pointwise convergent, which says, yeah, you can use a different n for every x. So if one works for all x's, certainly you're pointwise convergent, right? So I didn't explicitly state that, but hopefully that is clear. Just as if you're uniformly continuous, you're continuous, right? So this is also true. See if you can come up with an example of this where Fn converges to F, everything is differentiable, but their derivatives do not converge. And think about what can go wrong. Okay, if you want to come up with a counterexample, think about what can go wrong. Think about how something can oscillate. It can be very small in magnitude, but oscillate very quickly. That's sort of the key to coming up with this counterexample, is that you can have massively fast oscillation with very small magnitude. And that's going to be our issue with this. There will be a bit of a theorem which fixes it, but we have to impose a lot stronger restrictions in order to fix the differentiability issue with uniform convergence. But see if you can come up with these counterexamples. I give you one, see if you can come up with the other one. On Thursday, I will explicitly do this counterexample and give you an example for the other one. So if you don't do it, you're not going to miss anything. But it's a good little example to play with if you want to, just see if you understand uniform convergence. Okay, so that's going to finish it off for today. Ran a little bit over time. Thanks for your patience. Yeah, we'll meet up again on Thursday. I will cover this. Like I said, these sort of counterexamples, and then we might start series, like just start adding together these functions and see what happens. And I have to make a decision on whether I'm going to do Cauchy, because if I don't do Cauchy, I can't do the Weierstrass M test, and I really do want to, but we'll see. Game time decision. All right, so everyone, enjoy your Wednesday, and I will see you Thursday morning, bright and early. Yeah, sure. I might have to wave some things under the rug, though, if I do it, right? Just be like, yeah, this is true, or you can look this up or something. But let me get through the main stuff first, and then we can kind of, yeah, we can get through, we'll get through the main stuff, and then if there's time, I'll just be like, hey, and hand wave what I need to in order to get to the result I want. All right, everyone. I will see you Thursday.